It's a pleasure to have Márton Naszódi on our seminar. He is a comrade of several members of the lab, and mine in particular from good time we had. And he has recently done very interesting work on some topics that are between convex geometry and functional analysis, I guess. And this is what he's going to talk about today. Thanks, Márton, for giving the seminar.
Спасибо. Я буду рассказать сказку о функциональной форме эллипсоида Джона. Можно по-английски, Андрюшка?
Да, можно и по-английски.
Спасибо. Okay. So this is joint work with Grisha, and well, it's about the John ellipsoid. So my plan is that in the first half of the talk, my goal is to speak so that everybody can follow and get something out of it. The second half will stop at some point and have questions, and in the second half, that will be for say hardcore people who are very interested in the topic, and then there will be some third half as well, but I don't know yet what. So let's start with John's ellipsoid. So
just a small question immediately. Yeah. Can people interrupt you during the talk and ask stupid questions?
Thanks. That's a very good question. Absolutely, please do interrupt me. And second, I'm not following the chat or anything. I cannot see if anyone raises a hand. So I guess the best is if you have anything to say, to ask, to add, to contradict me, then just turn on your mic and shout. So yes, absolutely. Please stop me at any time. Yes. Okay. So the basic fact that we start from is the following. You have a convex body here. It's a triangle on this picture. Then you can take the largest volume ellipsoid contained in this body, and we call it the John ellipsoid, and it has all sorts of nice properties. Well, what kind of nice properties does it have? Well, first and foremost, it has a characterization using its contact points. So this is this well-known theorem of John. It says the following, that so BD denotes for me the unit ball, the Euclidean unit ball in d-dimensional space in RD, and so we can characterize the situation when this set, when BD is the maximum volume ellipsoid contained in K, and it happens if and only if we can find contact points, so points on the boundary of the body, which are unit vectors, so unit vectors on the boundary of K, and we can assign weights to them, positive weights, so that these linear algebraic formulas hold. Okay, where I is the identity operator. I'm assuming people are more or less familiar with this fact, and so yeah, that's John's condition. So now the question is, it's a general idea in functional analysis or convex geometry to go from convex bodies to log-concave functions. So when you have some fact about convex bodies, you want to ask if the same thing or something similar, something analogous will hold for logarithmically concave functions. So I guess I need to define it, or well, that's the definition. So function f is called logarithmically concave if this formula holds for n lambda. If you haven't seen it before, that's okay. I'll give examples very soon. But here is an equivalent formulation of this property, that the function is f is logarithmically concave if it can be written as e to the minus phi where phi is a convex function. And convex, it means it can actually take the value of infinity. That's fine. In that case, the value of f is just 0. And we like that. There is no problem with that. So why are they important, or why is the theory of log-concave functions, why is it an extension of the theory of convex bodies? Well, let me show you a few ways in which you can embed the set of convex bodies to the set of log-concave functions. Okay, so we fixed D, so we are in RD. And well, one obvious way to assign a log-concave function, to assign a function to a convex body, is to just take the characteristic function of your convex body. And it's quite easy to see that it is log-concave. It satisfies this condition. Now, another way to do it is to take a convex body which contains the origin in the interior, and take some exponent t. Imagine like t equals 1 or t equals 2, let's say, and you take this function, you consider this function. Now look at the second form of logarithmically concave functions. It's e to the minus phi, where phi is a convex function. And well, just put the k norm as a convex function. So if the origin is in the interior of k, then this k norm, it's a well-defined, the gauge function of k. It's a nice function. If k on top of having the origin in the interior is also symmetric about the origin, then this function is actually really a norm. If it's not symmetric, it's a non-symmetric norm, but it doesn't matter for our purposes. And you can put a little t here as an exponent, and this thing in the exponent will still remain a convex function. So one particular example is when your body K is just a Euclidean ball. And then you put, well, e to the minus x squared, and then this expression will be e to the minus x squared. And just so that it looks more familiar, we put this division by 2 here, and also some constant factor here, and then you immediately recognize the Gaussian distribution, the normal distribution. So that's again, well, based on this little fact, it's a logarithmically concave function. And here comes one more very important example, which is the following. Let S be a positive integer, okay? And take Rd plus S. So it's a higher dimensional space. And take a convex body in Rd plus S, okay? So we have this high dimensional convex body, and we take Rd, and we take the marginal on Rd of the uniform measure on this convex body. Okay, so I'm not talking about the projection of the body. The projection of the that convex body down there in Rd, it's going to be another convex body. That's not very interesting. What is more interesting is the marginal of the uniform measure on this convex body. And it turns out, and it's also not difficult to see, that this marginal will also have this property. It will be a log-concave function. Or, well, log-concave measure, to be precise. So sometimes we like to talk about measures or log-concave measures or log-concave functions. When I say log-concave measure, that just means that the density function is a log-concave function. Okay, so now the question is, great, we have the idea of the John ellipsoid for convex bodies. How do we extend this idea to log-concave functions? And Grisha and I, when we started thinking about this question, we soon ran across the paper of Alonso Gutierrez, Marino, Jimenez, and Villa, who considered this question and gave their answer. So let me now outline what they defined as the John ellipsoid of a function, of a log-concave function. So they follow the following procedure. First, for any alpha, take the super level set. Okay, so this is the super level set. So obviously, if alpha is bigger, oh, I'm sorry, I should have said this F norm, this is just the maximum of F, okay, or the infinity norm of F. Okay, so if we have alpha bigger than the infinity norm of F or the maximum of F, then of course this set is of measure 0 or empty, so then it's not interesting. So we take a non-negative meaningful alpha and take the super level set. Now, if F is a log-concave function, then it immediately follows that it's a convex set. So every super level set of F is convex. So you have a convex set, you take the John ellipsoid in this convex set. It's a convex set in RD. Now, consider, and then, well, if this John ellipsoid, it has a function, a characteristic function, and you can multiply this characteristic function by alpha, by the level which you considered, and then obviously this alpha times the characteristic function, it's going to be pointwise less than F.
Martin, sorry, so why stupid question, I guess, so why this body is convex?
Because if you have a log-convex, so that just follows from this definition. If you have a log-concave body, then it's what's it called? It's a pseudo-concave function or something like that. So that property immediately follows from here.
Mm-hmm. Okay.
You can, yeah.
Andrei, if you have a convex function, is it obvious that that level set is convex?
Yeah, and you can just look at
here
this.
you have minus log.
Here is the sub level sets, and for the e to the minus is going to be super level sets.
Okay.
Take the logarithm and you have a concave function.
Yeah. Okay.
Okay. And now you can ask. So let's get back to here. So for every alpha, for every alpha, you can take this function, this alpha times the characteristic function of the ellipsoid. You can think of it simply, take that ellipsoid in that super level set, and just give it a weight, the weight alpha. That's the weight that it deserves. That's what it has. And then the volume of this ellipsoid, the weighted volume of this ellipsoid with this weight is this, of course. And what they proved, so Alonso, Gutierrez, Merino, Jimenez, and Villa, so they showed that there is a unique alpha such that this expression is maximal. So you go with your super level sets. Of course, if alpha is low, your super level set is big. But also, so in the super level set, you get some big ellipsoids. But if you have a big ellipsoid in your super level set, but the weight alpha is small. Now, if alpha is small, then your super level set will be smaller, but the weight will be bigger. So it's not clear how you need to choose alpha. But there is a unique best choice for alpha, they showed. And as it turns out, this unique best choice is not a very small compared to the maximum norm of F. Okay, so they also gave this bound. And so this is, let me just use this notation for now. It makes little sense why this funny notation. The J stands for John. Okay, so it's the John ellipsoid of F, and for whatever reason we have this little 0 here. Okay, so this function is there. I just use this notation, and it turns out that, well, you
mean for that particular alpha, right?
For that particular, that's right, the best alpha, this unique best alpha. That's right. Yeah. So that's there. That's the Alonso, Gutierrez, Merino, Jimenez, and Villa. And from now on, I'm not going to pronounce their names over and over again. I'm just going to call it the AMJV ellipsoid. So this is really a function. The AMJV ellipsoid is a function. Okay, and now you can talk about the volume. So let's go back to convex bodies. So that's a classical question. What's the ratio of this best ellipsoid compared to the volume of this best ellipsoid compared to the volume of the whole body? Now, when you deal with functions, then instead of volume, you say integral. So you compare the integral of the big function with the integral of this ellipsoid, which is just this weighted volume right here, and they gave a bound on the ratio. So we know the order of magnitude, and they even discussed, they characterized the extremum case, both in the symmetric case, so when f is an even function, and also when f is not an even function. So just like in convex geometry, you consider symmetric convex sets and general convex sets. Okay.
And is
so
the
now,
ratio essentially the same as
it's
for
the same,
classical?
yes, up to this constant. Well, of course, there is this 1 over d here, but yes, up to this constant, it is the same. Yeah, it's this root d, just like the classical. Which, I mean, the classical result is. Yeah. Okay, so.
Can I ask one more question?
Yeah.
Sorry, Marci.
Absolutely.
So on the previous slide, so this, so when you talk about the volume of this ellipsoid, it's really just the volume with respect to, I don't know, uniform or like
Lebesgue, just Lebesgue measure volume, but then I multiply it with this alpha.
Yeah, okay,
right.
Okay.
So,
just the standard Lebesgue
yes,
measure.
Standard
doesn't
Lebesgue
have to
measure.
do anything with the function.
Not. That's right. Yeah, exactly. That's important. Yeah, doesn't have to do anything with the function.
Okay.
Okay. So, actually, that would be an interesting thing to measure this volume. But you see, yeah, no. I mean, you have to measure it. If you measure this volume with respect to the function, then this alpha will be, yeah. Anyway, so no, it's not a function. Okay, so I mean, that's the end of the story. There is a John ellipsoid for log-concave functions. What is there to say? Now, we weren't. We thought that there is more to say. There should be more to say. So first of all, let's consider the following example. So let me just go back to how we can create log-concave functions or log-concave measures. One is number 4 here. You take in Rd plus S is some positive integer, you take a d plus S dimensional convex body and take the uniform measure on it, and then take marginal on Rd. So, I mean, wouldn't it be natural to say that if I have an ellipsoid up there, or say the Euclidean ball up there in d plus S dimensional space, and I take the marginal, so this bar means marginal, the marginal of this measure on Rd, why is that not an ellipsoid? Or take the limit case when S tends to infinity and you properly scale your ball. Then in the limit on Rd, you will get the normal distribution, Gaussian distribution. That's, I guess we all know that. Why isn't that? Why isn't the Gaussian distribution a John ellipsoid? So the question is, take the Gaussian distribution on Rd. That's a nice, beautiful log-concave measure. But one would think that itself should be a ball, that itself is an ellipsoid, isn't in some sense. Why do we want to approximate it with some bounded set? Also, some minor thing that it's not monotone with respect to taking marginals. So if you take the John ellipsoid of some measure or some function, or you take the marginal of that function on Rk and then take the John ellipsoid, you may get something smaller. Another problem, and I would say this is the this would be the one that captures it the best. What did we really do? So let's go back to this definition. What we did was take the graph of your function, and we simply found some big volume cylinder under this graph. right? That's what it is. It's a big volume, or the biggest volume cylinder, ellipsoid-based cylinder. So, but why is it that the John ellipsoid is not an ellipsoid, it's a cylinder? And then the next question is, where is John's characterization from the story? So I'm trying to answer these questions. I mean, well, we're going to give a different definition. So, but before I give the definition, let me give some geometric motivation. So again, we go back to this example over and over again, that to obtain a log-concave measure on RD, the easiest, the cheapest way to do it is to take a convex body in RD plus S, where S is some positive integer, and take the marginal of the uniform distribution on this convex body. So you have the uniform distribution on the convex body. That's a measure on RD D plus S, and you take the marginal of this measure on RD. So here you took marginal. Here is the density function of this marginal.
Sorry, and in that case, just out of curiosity also, the log concavity follows from Minkowski's...
Oh, thanks very much. Very good question. Yes, this is, in fact, this is one way of phrasing the Minkowski inequality. Yes, then you have log concavity. It's the Minkowski inequality and or the Prokop-Leindler inequality. Actually, I think it's simply the Minkowski inequality. Yeah. Yes. That will say that. In fact, you can go even further back, and you can call it Brun's concavity principle. That's what's responsible for this. That this marginal will be log concave. In fact, I have to tell you the truth. The truth is that it's not just one example; it's all the examples. So it turns out that every log concave measure in RD can be obtained as a convex body in RD plus S if S is large enough, and just take the uniform measure on the convex body. Now, this is not true, of course, but it's true in the limit. So if you take convex bodies in RD plus S, and you take the uniform measure and take marginal on RD, then this way, and S goes from 1 to infinity, and for each S, you take all the convex bodies and all these marginals, then you get a dense set in the set of convex bodies, in the set of log concave measures. I'm sorry. So essentially, you can just think of any log concave measure on RD as a measure that comes from a D plus S dimensional convex body for a large enough S. So that's back and forth. Okay, so here is my convex body, and then what's the natural? What is a natural way of talking about the John ellipsoid of my measure down here? Well, just take the John ellipsoid here, and the John ellipsoid itself, it also has a marginal. So just take that marginal, and you'll find it here. But then it turns out that I can actually take a different convex body. Here, I'll explain what Schwarz means. It's Schwarz symmetrization. But all I want to say is that this body is not unique for my log concave function. So I can fix a log concave function and say that I want a convex body whose marginal is this log concave function. And then up there, maybe there is no convex body for RD plus S for a particular value of S. I have to increase S. But let's say for some value of S, S equals 100, there is a convex body for which this is the marginal, this fixed log concave function. The blue function is the marginal. But then there is others as well. Then in RD plus S, there might be other log concave, other convex bodies. So here's one way to kind of put them in a better position to somehow tame this zoo of convex bodies up there, which is take Schwarz symmetrization. So Schwarz symmetrization is the following: it's Schwarz symmetrization about RD. So here is RD, and we have some convex body in RD plus S. And you must have learned a Steiner symmetrization, which is if you have a A convex body, you take a hyperplane, you draw perpendicular lines to that hyperplane, you take these intersections with the lines and put those, you get the line segments, you put them in the right position so that the hyperplane is in the middle, right? And you get a new thing, which, as it turns out, is a convex body. It has the same volume, but is nicer because it's symmetric about the hyperplane. So Schwarz symmetrization is the same, but now it's not about the hyperplane, but about any linear subspace. So let's say you have RD, and you do Schwarz symmetrization about RD. In this case, for each point of RD, you draw an S-dimensional disk around that point, vertical to RD. So in RS, you draw that disk, such that the intersection, this S-dimensional section of the original body is of the same S-dimensional volume as that. Okay, so I started with some convex body up here in RD plus S, and I got a much nicer convex body, the Schwarz symmetral, which is now symmetric about RD, and then I could take. Of course, when I do the symmetrization, the ball becomes the ball of the same radius, so nothing happens there. And so I will still see this ball inside my function. But now I may be able to take a bigger ellipsoid. And I can take, so here's a bigger ellipsoid, and I can take the marginal of this bigger ellipsoid, this red marginal. And now that's nicer, that's bigger. So by properties of the Schwarz symmetrization, if you have an ellipsoid, after Schwarz symmetrization, you get an ellipsoid. By the way, it's not an obvious fact. It's a good homework. If there are students here, you can play with it a bit. How do you prove that you take the Schwarz symmetral of an ellipsoid, you get an ellipsoid? In any case, so here, the Schwarz symmetral, the John ellipsoid of the Schwarz symmetral will not be worse. It's not going to be smaller volume than the John ellipsoid of this one. So why not start with the Schwarz symmetral? Okay, but there are problems here. So one problem is that for this whole idea to work, S may have to be very large, because if I start with a log-concave function, this blue log-concave function, then it may happen that it comes from a convex body in RD plus S, but S is very large. If you take a smaller dimension, like smaller S, then you just won't find a convex body, which gives you your log-concave measure. And also, it only makes sense for integers, right? I mean, you want to talk about RD plus S. And here comes our solution. Just compress all this S-dimensional space into one dimensions. After all, if you do a Schwarz symmetrization, then there is really no need to represent this body in RD plus S, because it's symmetric, it's rotationally symmetric about RD. So you only need one extra dimension, RD plus 1, to encode this entire body. That's our idea. So let me formalize this idea. So here is the idea. So we have a convex body F, and we fix S, okay? And the S lifting of our function F, so F is this log-concave function, is going to be this. For S equals 1, this is essentially the graph, right? You more or less get well, it's not the graph, it's you take the graph, you take the symmetral of the graph, and it's the area in between, right? What is defined here. Now, if S is not 1, well, then it's something different. And the meaning of this is that I look at RD plus 1, keeping in mind that this last coordinate really stands for S coordinates. Okay, so that's why I have this 1 over S power here. And I define the S volume as well. So what's the S volume of a set? So let's say I have a convex body, let's say, in RD plus 1, which is d-symmetric. I will only, in RD plus 1, I will only consider d-symmetric bodies. I'm not interested in anything else. So take a d-symmetric set, let's say a d-symmetric convex set in RD plus 1. Now, if I put S equals 1 here, and I would say take this integral where this L sub x is the orthogonal line at x, which is orthogonal to RD, right? So if RD is the horizontal plane, then L sub x is take a point x in the horizontal plane and just take the vertical line at that point. Okay, so for each, if I just wrote you this formula that, with s equals 1, you would say, well, obviously that's one way of computing volume, right? It's Fubini's rule or something like that. So I define this thing, and I will call it the S volume of a D-symmetric set. Okay, so this is the S volume. So again, the idea of this definition is that I think of this last coordinate in RD plus 1, the last coordinate, I think of it as really encoding S coordinates. So when I see a line, a vertical line, in terms of volume, I see an S-dimensional disk there. That's why this power S. If you have an S-dimensional disk of radius R, then the volume is going to be R to the S, right? Some constant times R to the S. So that's why I have this S. Now, this is not a measure. I called it the S volume, but it's not a measure because, well, it doesn't even make sense for non-symmetric sets, not these symmetric sets. If you try to define it, I mean, the same definition for that's not the measure, but it's a nice functional. But now you can take the marginal of this non-measure. So what do I mean by marginal? I mean the following: that take a Borel set B in RD, and I fix C. So again, I want to fix C, and I will, for fixed C, I take this marginal of this, and I claim that this thing here, I claim that this S marginal, which I'll define in a second, it will be a measure. So what is this S marginal? I have to tell you what the value is for a Borel set. And well, I just do this integration over B. And now I'm not trying to measure sets in RD, RD plus 1. I'm measuring sets in RD, and this is a measure, and it's not hard to see. Okay. And so if you look at the definition, so now let me go back to the definition of the S lifting. So this is the definition of the S lifting of a function. Well, here is the picture. Then if you weren't able to follow it so closely, that's absolutely fine. But the point is, if you just look at these definitions, then you can see that the S marginal of the S lifting of F is F itself. Okay, so S lifting and taking S marginal, these are reverse operations, in inverse operations. So I take a function, I think of it as a density function, I think of it as a measure. You take the lifting of this measure, this is the S lifting, that's a convex body up there in RD plus 1. And then I turn this is like C bar. And then I take this convex body in RD plus 1 back into a measure on RD. Right? And if I do that, then I get back.
There was a comment. There was a comment.
My comment, it wasn't convex. The set is not convex, and this.
Yeah. I'm sorry. Yeah. Not convex. Sorry. Yes. This is not a convex body. It's a D-symmetric set. Yeah. Right. Like here, it's not convex, but it's a D-symmetric set up there. Yeah, that's right. That's actually very important that it's not convex. And the other fact is that if I take any set, I just put an E here. If a set is a subset, so this is, let's say you have two D-symmetric sets, which is a subset of this S lifting, then if I take the density of the S marginal, then it will be pointwise less than F. That's again obvious. So there is nothing here, nothing to prove. You just look at the definitions. Okay, so these are our basic notions. So the S lifting, which is how you get from a function, you get a set, a D-symmetric set in RD plus 1. And the marginal, which is you have a set, the S marginal. You have a set, a d-symmetric set in Rd plus 1, and that gives you a function on Rd. Okay. And so now we'll define our John ellipsoid. So we'll define a John ellipsoid for every S. So that already shows that we are better than AMJV because we have one ellipsoid for every S. That's more ellipsoids than just one, right? So I'll be a bit more specific than that. So take for each S, fix an S, and take the maximum S volume ellipsoid among all ellipsoids contained in this lifting. Okay, so you do this lifting. In this lifting, you can consider nice d+1 dimensional ellipsoids. All of them, I'm only interested in ellipsoids which are symmetric about Rd. Okay, and take the one which has biggest S volume, S volume as defined here. Okay, and that's what we will call the John S ellipsoid of F. Okay, so take F, fix S, and then the John S ellipsoid, the John S ellipsoid of F will be this biggest S volume ellipsoid. And then I can turn it into a function by taking the S marginal. And now this thing is a set in Rd plus 1. By the way, every time I have a bar, that means that it's a set in Rd plus 1. So the bar means that it's a set up there. So for example, this is a set in Rd plus 1, the S lifting. But if I take marginal, then I get, what is this? This is not a set, this is a function. This is a density function in Rd. And some basic properties, if I take a constant, then multiplication by a constant, that's kind of obvious. Also, it behaves nicely with respect to affine transformations on Rd. So this John S ellipsoid. So first of all, I mean, I just defined it, but I have to state it that it exists and it's unique, and it turns out to be the case. So for every S, you fix S, and let F be a proper log-concave. So proper just means that it's topologically there is nothing nasty here. So it's upper semi-continuous and has a positive and finite integral. It's also important if it's, say, the constant 10 function, we don't want to, we won't try to approximate it with an ellipsoid. So it has to have finite integral. So we have a log-concave function and a fixed S. Then there is a unique John S ellipsoid. And moreover, it has this property that the maximum of this, so let me go back here. So again, the S marginal, the maximum of the S marginal has this property. That's the same property that the AMJV ellipsoid has. And in fact, this proof, I mean, the proof that it has this property is very, very closely modeled on the AMJV proof. That's a beautiful paper. So it's no question about that. Okay, so now I define this.
So sorry,
yes.
Márton. So it doesn't depend on S at all. This bound.
No, this bound doesn't depend on S. That's right. It holds for every S. Yeah. So now I defined all this nonsense quantities. What is this good for? So here I'll show you four results that we have. So one thing is that we have John's condition. So if S is some positive number, so we fix S. So all these stories start with this, that you fix positive S. So you fix S, then we can tell when we can give an equivalent. We can characterize the case when the d+1 dimensional ball is the S, is the largest S volume d-symmetric ellipsoid contained in the S lifting. In other words, when this ball is the John S ellipsoid of F. So what is the characterization? It looks very much like, so let me just go back. So what was John's theorem? So this is about convex bodies. If I have, I need to have contact points so that these conditions hold. And now in our case, we have the same, we need to have contact points. I put a bar up here, again, stressing that we are in RD plus 1. So we have these contact points up here between the boundary of this S lifting and well, they are unit vectors and positive weights so that it holds. But up here, we have I plus S and not just the identity matrix. So it's the identity, it's the D by D identity matrix, and plus it has to be a D plus 1 times D plus 1 matrix. So it's a diagonal matrix with 1, 1, 1, 1, 1, S. Okay, that's what's written here. Okay, so that's one result. So we understand we have John condition. The second is that what if S tends to 0? So our definition, let me just go back here. So all these definitions, they make sense if S is bigger than 0. So we had to have this as bigger than 0 condition. But nevertheless, you can ask what happens when S tends to 0. And the answer is, and this is now why we call it the J0. With you will get back the AMJV ellipsoid. So for S tends to 0, it is that ellipsoid. So here's the theorem that F be a log-concave function. Then you can find an A and an alpha such that, and the translation vector A in RD, such that if you take this ellipsoid, so this AB plus little a, this is an ellipsoid, and times alpha, then this thing will be less than pointwise less than F. And your functions, the John S functions as S tends to 0 will tend to this characteristic function. When I say tend to, it means that they uniformly converge on the complement of any open neighbor. So the point is, in some sense, it's a very strong convergence property. And this is exactly the AMJV ellipsoid. So it will coincide with what they define. And now, as a corollary, and also using some bounds on the ratios of S ellipsoids, we get the volume ratio bound for John S ellipsoids. So this is not independent of the AMJV result. It relies on it.
May I ask a question?
Yes.
What does your criterion, your characterization of John function say in case S equal to, when S is equal to 0? Does it say anything in this case?
It's a little difficult to say because as S varies, the meaning of this ball changes. So if so I guess that would say something. Well, I mean, it would say something like this: that the unit, so that the cylinder. So you take the d-dimensional unit ball and the unit length, the unit height cylinder over this ball that's contained in F. That would be the case.
Marty?
So yeah, I'm sorry. So let me answer Igor's question. So in that case, what it means is that these are horizontal vectors. So you will have they will be in RD, and they will give you the identity.
Why in RD? Aren't they on the top of the cylinder?
No.
They will be in RD.
They will be in RD. They will be horizontal.
Well, that's strange.
No, may I comment?
Yeah. Okay. Go ahead, Krisha.
The thing is that there is no such condition even in one direction for this AMJV ellipsoid, and that actually was one of the main points we started to develop all this technique or whatever you call it. And so in they in their archive paper they put they write about some John condition, but it's actually the same to say that okay, we have a John
for the level
ellipsoid
set
inside the super level set.
Yes.
And
Yeah.
that's
So
all.
if you go back here, yeah, exactly. What the only John condition that they can give is that, well, what do? They take the super level sets, and then of course it will be true that first the super level set John's theorem holds. That's a d-dimensional fact that then everything is flat.
Okay,
Everything
so
is
I wonder if it is an interesting question to see how these contact points behave as
SS goes to 0. I'm not sure. I mean, my guess is that, I mean, we know that there is this AMJV ellipsoid. We know that our ellipsoid will tend to that. I think at the end you just get this obvious d-dimensional thing that you have some level set, and they will tend to the John contacts of that level set or super level set.
Well, okay,
so yeah. Okay. Oops. Okay. So now this is about the limit as s tends to 0. How about s tends to infinity? Well, so this is the case when Gaussian measures come into play. So as long as s is not infinity, our John S ellipsoid or the John S ellipsoid function. So let me just go back here. So you take the John S ellipsoid. So this is a d+1 dimensional ellipsoid, and this S marginal is a function. Now this is this function on RD. So as long as your S is finite, it will be, you have a compact set up there, an ellipsoid up there, and you take the marginal of this ellipsoid. Wow, that's a compactly supported measure. But once S tends to infinity, you can talk about, you can approach the Gaussian density. So first of all, we say that if you have a log-concave function, then there is a Gaussian density. Sorry, if there is a Gaussian density, which is pointwise below your function, then there is one which is a maximal integral. And also, if you take all those Gaussians below f, pointwise below f, that are of maximal integral, they are all translates of each other. And watch out, I didn't say that it's unique. I didn't say that if you have a proper log-concave function. So it's a finite integral. We're talking about positive finite integral function. And assume that there is a Gaussian density below it. It's not true, right? For every proper log-concave function. Take any compactly supported log-concave function, right? Take the characteristic function of the Euclidean ball, or take a big dimensional Euclidean ball and the marginal of it. You will always get compactly supported measures. So there's going to be no Gaussian density under them. But if there is, well, for some log-concave functions, there is a Gaussian density below. Then there are some that are of maximal integral, but they are not necessarily unique. And it turns out that it's not just that we couldn't prove unicity, but it's not true. And I'm looking at the time, and I have the feeling that I'm not going to explain you this example. You can check it. Okay, so we know that if there is a Gaussian density under f, then there is one or more of maximal integral. But now, when is there a Gaussian density pointwise less than f? And then the answer is that look at our John S ellipsoids, and if their S measures tend to some positive number, this lim sup is positive, then there is a Gaussian density below f, and it's an if and only if. And in this case, so let's assume that there is a Gaussian density below f. Then, first of all, this lim sup is really a limit. as s tends to infinity. And second, and this is the real nice fact, our John S functions tend to one of these good Gaussian densities. Well, in the sense that there is some sequence of SI that tend to infinity, such that those John SI functions, they tend to G in some really strong sense. This convergence is some good strong convergence, and G is one of these good Gaussian densities. So this is one of the maximum integral Gaussian densities below F. So that's our result number 3, and here's the last result, number 4, which can be phrased absolutely independently of anything that I said before. So forget the functional John ellipsoid, forget S measure, forget all this. You can phrase this question. So it goes back to this geometric theorem, this nice theorem of Bárány, Kacsaszky, and Pach. So they proved that it's a Helly-type theorem. So what's their quantitative Helly-type theorem? It says that take a finite family of convex sets. Then you can take a subfamily of size at most 2D, such that if you take the intersection of that subfamily, then the volume is not going to be that much bigger than the volume of the intersection of the original family, right? So that's their result, and then they gave a bound for this C sub D. They gave something of order D to the D squared, and said that it should be D to the constant D, which a few years ago I proved D to the 2D. And then Brasitikos building on that proof, he improved it. He used a very nice idea and pushed this exponent, this constant 2, down to 3/2. The point is, for now, you can forget this quantitative bounds. The point is, I have finite family convex sets. I can select 2D of them, such that the intersection of that 2D, somehow the volume is, well, up to a constant factor, depending on the dimension only, away from the volume of all the sets. That this Helly number 2D is optimal. So that again is a little homework. If you want to play with it, if I put 2D minus 1 here, then there is no constant. That's an easy exercise. So now we looked at the same question. What would be the same question for log-concave functions? Well, I have to talk about intersection, right? So here I had intersection of convex bodies. What would be the analog for convex functions? Well, I guess it's very natural to talk about pointwise minimum. Okay, so if I have a family of convex functions, so sigma is some set of indices. So, then I can talk about the pointwise minimum of that set of functions. And here is what we found. So take a finite family of nice log-concave functions. So they are upper semi-continuous log-concave functions. And we define this f sub sigma this way for any subset. So then you can choose 3D plus 2 of them, or maybe less, so that if you take only those 3D plus 2 and the pointwise minimum, then the integral is not going to be that much different from the integral of f. So there is some dimension-dependent constant here, and this d to the d, this d to the big O d, this is a good constant. I won't explain it now, but sorry. Like here, this d to the constant d, it's as good as it can get. You can have the constant better, possibly 1/2 d is also true, but you cannot get constant to the d here. So it has to be d to the big O d. So this is a good constant times the integral of pointwise minimum of all of them. Okay, so F is the pointwise minimum of all of them. Okay, so it's like the intersection. So here you have the intersection of all the sets, the volume, and here you have the intersection of only 3D plus 2 sets. Okay, so this is our fourth result, and I want to stress that here for this result, it's not about John ellipsoid. It's not about nothing. It's you can phrase it without any of that introduction, and so but you notice that here we have 3D plus 2 and not 2D in this original theorem of Bárány, Kacsowski, and Pach. There is this 2D, and we know that that's optimal. So why do we have this 3D plus 2? Well, the answer is it shouldn't be 3D plus 2. We know that we can actually prove the same result with 2D plus 1, but then the volume bound becomes ridiculous. So then we won't have this nice bound here, but we will have more like d to the d square or something like that. So we can go down to 2D plus 2, and we can show that you cannot go below 2D plus 1. We cannot go below 2D plus 1. And here is the example, and just like with the previous example, I'm not going to explain this example, but it's again rather simple. It's a very, very simple example. The point is that in a way it's funny. So from a, I don't know, combinatorial point of view, it's funny because it says that so for convex bodies, this Helly number is 2D. And for log-concave functions, this Helly number is 2D plus 1. So it kind of suggests that log-concave functions are d plus 1 half-dimensional convex bodies. So in some sense, that's a good way of looking at them. And so here is, I think, a good point for me to stop and have questions, and then let everybody go who is not interested in the proofs. And then my plan is to only outline the proofs. So I'm not planning to talk for another hour, but I don't know, another 20 minutes or maybe even less, depending on interest. So questions up to here. To this point.
So for this quantitative Helly-type result, is there a better understanding of, even for convex bodies, how does this volume bound depend on the number of that you substitute instead of this 2D?
Yes. So if you increase this Helly number, then it's in a way it's well understood. So first of all, if you're willing to have exponentially many here, so instead of 2D you want to say 2 to the d, then your constant here will be very small, and then
very small, meaning independent of d,
meaning, okay, I can say something like this: for every epsilon, so if you only allow a 1 plus epsilon error here, there is a constant depending on epsilon, which would be, say, 1 over epsilon or some. I'm bluffing here. Let me just say there is a constant, but a constant that we have control over, so that if you take constant to the d, if you put constant to the d here, then here you only get error 1 plus epsilon. Okay, so that's the, so you can think of it as an approximation result, right? So if these convex sets were half spaces, then we're talking about take a polyhedron, and you have to approximate this polyhedron with a bigger polyhedron, but you're only allowed to use its own facets, right? You cannot just find some good supporting planes, but you have to use the original defining inequalities. And you have to just throw out some of the inequalities and only keep a few. Yeah. And then if you can keep constant to the d many, then you get, and that's fine approximation. And there are results about rough approximation. A similar result is very easy to prove if you're allowed to have d squared, for example. So to prove the same result with d squared, that's a kindergarten exercise. But you can do things in between. Yeah. But no, I mean, in general, in between, I wouldn't say it's well understood what you have if you have d to the 5th power versus d to the 10th power. But
in particular, is it clear when CD becomes exponential?
Yeah, when CD becomes, you mean, oh, when CD becomes exponential. I don't know. That's a tough one. I can't answer that.
Okay.
I don't know. That's an interesting question. Yeah.
And in your case, what kind of bound do you get for 2D plus 1? You said that it's 2 weeks.
So yeah,
but what does it mean?
We computed it I mean, not very recently, but it's something. As far as I remember, it's either d to the d squared or d to the d cubed, something like this.
Even worse, Marcy.
No, it wasn't. It wasn't d to the d to the d.
It was d to the d to the 5th, something like that.
Yeah, d to the d to the 5th. So d to the polynomial d. Yes.
Okay. Okay.
Yeah. But we really believe it should be d to the constant d. At least I strongly believe that. But that requires some nice idea. Yeah.
Okay.
I have a question.
Okay, Grisha.
Where is the main geometric corollary of the John theorem?
I didn't want to go in that direction. The containment. Yeah.
Oh, I mean about touching, well, supporting log linear functions, all these stuff.
Okay. Sorry.
Okay, let's go further.
Well, at least one of the co-authors knows what's it about. Any other questions?
Okay. Any other questions? Then I'll go on and talk about the tools. Okay. So here is one of our. So I'm going to introduce 2 tools, and then show you how to use them in the proofs, but only at the very high level explanations. I'm not going to go into detail. So we have 2 ellipsoids, and we can talk about interpolation between ellipsoids. So in convex geometry, when you deal with convex sets, you can talk about, so let's say this ellipsoid was A1b, you can have a translation vector, that doesn't matter. This one was A2b, so these are the linear transformations, and then you can take the average of the linear transformations. You get a new ellipsoid. Now, when in our ellipsoids, an ellipsoid is encoded by not just the matrix, we have a d by d matrix, and we have a number, which you can call the height of that ellipsoid. This is how you get a d-symmetric ellipsoid, because again, it's important, we only deal with d-symmetric convex sets, or d-symmetric sets, d-symmetric ellipsoids. And how do you define, let's say, an origin-centered d-symmetric ellipsoid? Well, you have, you tell me the d-dimensional ellipsoid, you can call it the base, and the height of your ellipsoid. So to give a d-symmetric ellipsoid, you give a matrix, a d by d matrix, and also the height. So now here comes the idea that for the height, we don't take the average, but we'll take this geometric mean of the heights. Okay, and here is a little formula about how to compute the volume of such an ellipsoid. So if you have an ellipse, actually I should have the BD here. So the S volume of an ellipsoid given by this matrix A plus alpha, it's easy to see that an alpha scaling, so vertical scaling, changes the S volume by a factor alpha to the S. And then we have the usual determinant of alpha. And let's look at this so-called interpolated. So we called it the interpolated ellipsoid. So the measure, the S measure of the interpolated ellipsoid is bigger or equal than the geometric mean of the two ellipsoids. Okay, so in particular, if they were equal, then unless these matrices are special, it will be actually bigger. And the determinant here, so this determinant is again bigger than that's just a basic fact from linear algebra. Okay, so what we'll use, so one tool we have is that you have two ellipsoids, then you can create a third ellipsoid somehow in between. And the second tool is bounding a function f. So one thing is that whenever you have a log-concave function, you can take this bound, e to the minus theta norm x, for some theta and theta, little theta, capital theta, that depend on f only. So for every log-concave function, you can bound it with a proper exponential function. But we have a much finer bound, which is the following. So let's say that you have a function f and you fix s, and and assume that the ball, the d plus 1 dimensional Euclidean ball, is in the S lifting. And take a contact point, and this is very important. This contact point is not in the horizontal plane, so it's not in RD. It cannot be horizontal. So take a contact point of BD and this S lifting of F. In other words, well, this is the contact point, but again, not horizontal. Then we have a bound, and you don't have to read this formula, I'll explain it in a second. Then we have a bound on F globally. So I just look at one point, so just local fact that this ball is inside, that's a global fact that the ball is inside the S lifting, but locally there is this one touching point. Then globally, I have some sort of exponential bound on F. So it's going to be a proof of this, but you can think of it as a proof, or you can just look at it as kind of more or less explaining the formula itself. So here we have our log-concave function, this blue function, and the ellipsoid, this green function is the the margin of our ellipsoid, and we look at a contact point, so a point where they touch. Now we're talking about log-concave functions, so take the logarithm minus logarithm, and we get convex functions, right? The blue function is bigger, so the minus log will be smaller, and we still have this contact point. But it's convex, so since it's convex, it has this property that you draw the tangent at this point, and then the function is above. Both functions are above. And well, this tangent here, when you take e to the minus, that gives you this exponential function here. And that's all that's written here. And you use it with g being the ellipsoid. And so now, using this, let me just give the sketch of the proof of two, let's say two of our kind of well, I would say sexiest results, or sexy results. At least easier to show results. One is the Jones condition. So how was Jones condition proved for convex bodies? So first, now I'm just recalling from the theory of convex bodies. How do you prove Jones theorem? So here's the theorem. The theorem says that, sorry, that's not where I wanted to go. So for convex bodies, the theorem says that there are these contact points and weights that satisfy John's condition, if and only if, well, sorry, this is an easy fact that those contact points and weights, they can be interpreted as I0 being in the convex hull or being in the positive hull of our UIs or UI tensor UIs, and then something is in the positive hull or not in the positive hull if there is a separating hyperplane. It's a positive cone, and this one point in the I0 is separated by a hyperplane, then it's not from all those points, then it's not in the in there. And so John's theorem could be rephrased this way, that if I0 is separated from all these matrices, these are not really matrices, matrix vector pairs, if and only if the ball is not the maximum volume ellipsoid. And so John proved this direction. He proved that if the ball is the maximum volume ellipsoid, then I0 is in the positive hull. In other words, then there is no separation. So the way I wrote it, it's the left to right direction. So how do you prove it? Well, you say there is separation, then there is a separating vector, a normal vector of the separating hyperplane, and that normal vector helps you do a local perturbation of the ball to get larger volume. And now Keith Ball used, so Keith Ball's direction is the opposite. So he proved that if the ball, so that if there is no separation, so in case if you can write I0 as a proper as a positive combination, then the ball is the maximum volume ellipsoid. So how did he do that? So he said that, well, assume that there is a bigger ellipsoid, and then we want to show that then there is separation. And the way to do it is that he said that take this hyperplane with this normal vector, and then it will separate. And here it is used that this line segment of ellipsoids. So if you take a perturbation of an ellipsoid, so you start with the identity, so with the ball, and then you just move it towards A. This is also contained in your convex body. If I have two ellipsoids contained in a convex body, then their convex combination is also contained in the convex body. This is an essential part of the proof of this direction. What do we want to prove? We want to prove something similar, except that instead of having just the identity, we have I plus S here. That's, now I should really go back to the theorem. So our theorem says that you have that this UI tensor UI, it gives you I plus S. So now we have I plus S, and the origin, we have the same separation result. And again, to prove this direction, which is John's theorem, so if BD plus 1 is maximal, then we can write it as a convex combination or positive combination, which, writing in separation language, is left to right. It's more or less the same argument, local perturbation. But interestingly, if you want to prove Keith Ball's direction, then you run into a problem, namely that now you cannot just say that take this line segment connecting the identity with A, or this ellipsoid with that ellipsoid, just take the convex combination of the two ellipsoids, you get the bigger ellipsoid, and that will be in between. It will be contained in the S lifting of F, and it's bigger volume, and we're happy. We have that originally wasn't the biggest. It won't work because here's the point: this S lifting is not convex. It's not a convex body necessarily. So here comes our interpolation between ellipsoids. Again, don't look at the formula. You can check it later. That helps us out. So that was this John condition. So in this John condition, again, our main tools was this tricky interpolation of ellipsoids instead of just taking line segment. And now the second thing I want to give you a proof about is this quantitative Helly proof. So so here's the obvious approach. We have the quantitative Helly theorem in our d plus s, right, for any s. So just take the d plus s dimensional result and say that, well, my functions down here in Rd, they are just marginals of d plus s dimensional convex bodies. If s is large enough, then these convex bodies, these marginals, approximate all our functions well enough. And then up here, we can just apply the d plus s dimensional result. But the problem is that s may need to be very large, and the d plus s dimensional result is a bad result for Rd. Well, to begin with, the Helly number is not 2d. The Helly number is 2d plus s. That's bad. So you have to do something smarter. And so here's the idea. So we'll try to copy the proof the d-dimensional result, the proof that gives this bound d to the 2d, but at some point we'll see that it stops. We have to do something more. So what we do is, first we say that assume that our function is in joint position. Okay, so that and we take the 1 lifting. So s equals 1 in this whole game now. S equals 1. Okay, so we assume that our function is in joint position. In other words, the d plus 1 dimensional unit ball is its joint ball. Okay, in s equals 1 lifting. Then take contact points. Okay, so the function, I didn't draw the function here. The function, the 1 lifting of the function touches the ball at these contact points. Okay, and you can use the Dvoretzky-Rogers theorem to find d plus 1 contact points that span, that define a big volume simplex, not very big, but something of good volume, which has some we have control over its volume. We know that it's not too small. So there is the Dvoretzky-Rogers simplex that gives you d plus 1 points, and with some tricks, I'm not going to, I don't want to repeat the whole geometric argument. You find another d plus 1 points, and they together, these 2d plus 2 points, give you a convex body, which, as it turns out, contains a not so small volume origin-centered convex body. So using the Dvoretzky-Rogers lemma, we find a convex body which is contained in this convex hull of a few contact points, 2d plus 2 contact points. So far so good. And then we just use polarity. So here we have this origin-centered convex body with big volume, well, relatively big, we have a lower bound. So take the polar, then we have that if the blue set, the convex hull of the contact points, contains the orange set, then the polar of the blue set, which is this nice green polyhedron, is contained in something which is not too big volume, which is the volume of what is bounded from above. And we would be done. Well, almost, except that the problem is that if you look at only these functions that support these contact points give us, their graphs, what they bound, it's not exactly the green polytope, it's actually bigger. So you can see that these are just log-concave functions. They are not concave functions. So you don't have So these hyperplane, they may go above these hyperplanes, like on the figure. So this is what we have to deal with. So again, the polar of this blue set, which is the green set does not contain this pointwise minimum. Does not contain the intersection of these one liftings. And here comes the idea that luckily these functions will give us something because of our contact gives bound lemma. So let me go back here. So we had this lemma that said that if you have a contact point, so if the Euclidean ball touches your function at some point, that gives you some sort of exponential bound on this function. What it says is that if you go away, far away from the contact point, so here is the contact point, here is this touching the gradient of F1, if you will. And if you go far, far, far away, your function is small. That's what this lemma says. So that takes care of the integral of this of the function far away. But But then there's also the problem of what happens inside. So what happens close to the origin? Maybe we have some big volume here that these red functions will not give us anything very small in here. And then we use this bound that we have, that the S volume, what for S equals 1, the John 1 function is not of the norm of the John 1 function is bounded from below by the norm of F. But in order to get this norm of F, we have to add another d+1 functions. Here I don't well, this is again not difficult to see. This is now actually about convex sets, intersection of just convex sets, super level sets, and that's the rough sketch of this proof. Thank you.
Thanks a lot, Martin. I'll applaud the join. So, any question at this stage from experts? I guess that was this part
do you
for
have a question.
for experts
to know.
I think that I have a suggestion, not a question. So
Okay.
probably we can prove this Helly-type result for convolution, for the convolution.
Yeah, maybe.
Would be much more interesting.
Yeah. Now, for me, this is interesting. How to get that volume bound down, because I very strongly believe that this fact. I mean, we have to add these d+1 functions. Simply, there is no way. I mean, at this point, we don't see how to deal with these.
Okay, and I want to add another comment about this log-concave function. So why it's so important, and not only in convex analysis or now asymptotic geometric analysis, because actually this function, log-concave function, is a natural limit of several procedures in probability theory or even quantum mechanics, information theory. So if you're averaging something, then distribution, for example, some distributions that typically the limit will be something log-concave, convex or log-concave. That's the idea. So if you just look at Wikipedia on the list, there is a list of all log-concave distributions that I think that most of distributions that you know, they are log-concave. And it's not a coincidence.
Mm-hmm. I wanted to ask actually a question about, so you said that you have this bound for 2D+1. with Helly number 2D plus 1, does it the proof? Does the proof? I mean, it should be something else, because here you just use the first 2D plus 1 functions, and it already will give you some bound.
Yes,
basically?
yes. If we yeah. So that's not a totally different proof, but the problem is these points inside and the part inside. Yeah.
Mm-hmm.
So we have some very weak control over it unless we add these extra d plus 1 points. From a true functional analytic point of view, I guess this is not an interesting question at all, because, well, 2D plus 1 or 3D plus 2, these are the same, right? I mean, it's linear, but I don't know, from a combinatorial or convex geometry point of view, this is interesting. Like, what's the smallest case? What's the smallest Helly number?
I would say that this John's theorem, it gives kind of the same contact points, actually the same type of contact as in the original setting. And the thing is that in the original setting, we have different techniques how to work with these contact points. So starting with the Braskamp-Lip inequality or this and the Kidd-Bolz results, and here for this setting, I guess that one needs to develop a similar technique. That's all. So we don't know yet how to write inequalities with these functions. That's the problem from my point of view.
Okay. Any other questions?
Yes. I had a question about the part that you were talking about, the limit from S going to infinity. So you had.
Let me go there. So S. Going to infinity. Yes.
So do you understand well which Gaussians you can get by these limits?
That's an interesting question. Do you mean what do you mean which Gaussians? If we have multiple maximum volume Gaussians?
So
that's a good question. No. I mean, it should be some Gaussian in the middle in some sense. If you have like some family of Gaussians that are all maximal. If you have some family of maximal Gaussians, this one that you should get with this as a limit of these S ellipsoids. First of all, I mean, we don't have a result that would say that would say that it's not possible that for some SI the ellipsoids tend to one Gaussian, and for some other sequence of SI the S ellipsoids tend to another maximal Gaussian. So even that is not impossible at this point. That's just a wild guess that there should be some canonical Gaussians, some best maximal Gaussian, somehow the middle, some Gaussian somehow in the middle, whom all of them, any sequence should converge, but we don't have that.
Marci, may I comment?
Yeah.
So the funny thing, there are 2 points. The first point that we do not know how these limits behave. So yes, it's what Márton just said. Another point that if we consider the dual problem, so when we want to cover by the by Gaussians, yes, then if you can write the similar characterization when you can cover your function by the Gaussian distribution, and in this case, it will be unique. So, and this kind of extremely weird. So for the dual so here what is the optimization problem here is then we consider a log-concave function and we are looking for a Gaussian distribution that is below this function, yes, and we can prove that if it exists, then the solution exists. It's not necessarily unique, and it's, I mean, in the dual problem, if you consider log-concave function and you are looking for the Gaussian that how to say cover, yeah, pointwise bigger or equal than the given function, then the solution, if it exists, it's unique, and it's kind of extremely weird, and we don't understand. Honestly, we don't understand what is happening here. So probably there is something in duality or in other sense, but at the moment we don't know.
Yeah, thanks Marcy for a great talk.
Thank you very much.